So for section 7.5, we're looking at still trying to integrate our ratios or fractions. And another technique that we have to be familiar with is by using a partial fraction decomposition to break up these fractions into two smaller fractions. So if you remember back from pre-calc that you can take a rational function and we can break it apart so it's written as sums of partial fractions. This process is called partial fraction decomposition. So basically we're taking a fraction and we're trying to break it apart into two fractions that were added or subtracted together to give us the fraction that's in the integral. So for example, what you first need to make sure you do is factor your numerators and or your denominators. So in this example, it's already factored for you. So to go over remembering partial fraction decomposition, what you want to do, notice in the denominator you have two factors. So we're going to split apart the denominator into two separate fractions. So we want to figure out what two fractions were added together. One denominator would have to have one of your factors of x minus 1. The other fraction would have the denominator of x plus 2. Since these denominators are both x to the first, they're linear, then we're only doing partial fraction decomposition for proper fractions. In other words, we want these fractions to be in proper form, which means the degree of the numerator has to be less than the degree of the denominator. So these numerators have to be constant. So a and b are constants. So then what we're going to do is we can look at this equation. Imagine multiplying everything by your least common denominator, which is your x minus 1 and x plus 2. So this Heaviside method basically is now looking at this x minus 7 is equal to a times x plus 2 plus b times x minus 1. So what we're going to do is we look at each factor, we're then going to plug in the zeros for each factor. So in other words, we're going to let x be equal to 1 and plug it into this entire equation. So with 1 minus 7 is equal to 3a. So then a is going to be equal to negative 2. And then you do the same thing for the other factor, which would be your negative 2. Plug in negative 2 for x. So negative 2 minus 7 equals, notice this negative 2 plus 2 goes to 0, which is what you want. And then negative 2 minus 1 is a negative 3. So negative 3b is equal to negative 9. So we end up with b is equal to 3. So now we know what the numerators are going to look like. So we can plug these a and b values back into this equation. So I know if I actually take these two fractions and add them together, it's going to give me this larger fraction. So when to use partial fraction decomposition? So think about the types of integration we've been doing, u sub. So obviously u sub's not going to work. What you do is you look at your denominator, and if you can factor the denominator, that's when you're going to be looking at using partial fraction decomposition. So when you start these particular problems, just like we've been doing, if there's a constant we can pull out of your integral, go ahead and pull it out. So I have 1 over. Now notice this denominator, x squared plus x minus 12, can factor into x plus 4 times x minus 3. Again, when you look at this problem, we know a u sub's not going to work. You really would not want to do completing the square on this because you can factor. So now what we want to do is we want to break apart this larger fraction into two smaller fractions. So I'm going to do my partial fraction decomposition. So this is going to be equal to some numerator, which I'm going to call a, over one of the factors in my denominator, plus b over the other factor in my denominator, which is x minus 3. Multiply everything by the common denominator. So I have 1 is equal to a times x minus 3 plus b times x plus 4. So now to solve for a and b, I'm going to look at x minus 3, and I'm going to choose the 0 here. So I'm going to let x be equal to 3, and plug 3 anywhere in here for x. So 3 minus 3, that goes to 0, is equal to 3 plus 4, which is 7, times b. So b is equal to 1/7. Look at your other factor, which is plus x plus 4. So I'm going to let x be equal to negative 4. So I have 1 is equal to negative 4 minus 3 is a negative 7a, and negative 4 plus 4 goes to 0. So a is equal to negative 1/7. So now I know what these numerators look like. So now what I can do, instead of having this one larger fraction in my integral, what I can do is I can now rewrite this as the sum of two fractions. So again, remember I found a to be equal to negative 1/7, so I'll plug that in for a. So negative 1/7 over x plus 4, plus plug in 1/7 for b, so 1/7 over x minus 3 dx. Now what you want to do is you want to use your property of integration. Again, we're going to split up this integral into two parts. So I have 5 times your integral negative 1/7 over x plus 4 dx, plus 5 times your integral of 1/7 over x minus 3 dx. Before you yank out the negative 1/7 and 1/7, you want to make sure you split this integral. So now notice I can pull out the negative 1/7. So 5 times negative 1/7 will give me a constant outside this integral of negative 5/7 times your integral of 1 over x plus 4 dx, plus I can pull out the 1/7, and 5 times 1/7 is 5/7 times your integral of 1 over x minus 3 dx. Now it's set up and we can go ahead and integrate. Notice now I know the integral of 1 over x plus 4 is just going to be the natural log. So negative 5/7 times the natural log of the absolute value of x plus 4 plus 5/7 times the natural log of the absolute value of x minus 3 plus c. Now the one thing with these answers, you're going to end up with a lot of natural logs. When you're checking your answers, properties of logs may come in. You can write this answer in a couple different forms by using your property of logarithms. We can rewrite this as a product. So these answers may be written in different variations. So you take a look at another one. So here's my integral of 5x minus 5 over 3x squared minus 8x minus 3. Again, you want to factor wherever possible. I can factor a 5 out of this numerator. So I have a 5 as my GCF. So I have 5 times the quantity of x minus 1 over. You can factor 3x squared minus 8x minus 3. That's going to factor into 3x plus 1 times x minus 3 dx. So you do have a constant you can pull out of this integral before you have to rewrite this as a sum. So I can rewrite this as 5 times x minus 1 over 3x plus 1 times x minus 3.